So last year you took a little bit of a look at electric currents and circuits and how those worked. And this year we're going to do a review of the pieces that you looked at last year, as well as getting into some of the details about what happens in various situations. So we looked at electric potential earlier in the way of voltage and in the way that it worked within an electric field. And now we're going to take a look at that in the same sort of way, but within a circuit. We know if we have a positive plate and a negative plate and we put a charge in there, it will be repelled by one plate and drawn toward the other. And the same idea applies to a circuit. We have a battery that has a positive end and a negative end, and then that wire connects those two sides of the battery. So essentially, it's like taking the situation that we had before and spreading it out and keeping it, containing it along that wire. So it's not a full field, it's just what's happening on the wire. And so we know that electrons are what is moving when we have electricity. And so the electrons are repelled from the negative side of the battery along that wire and then drawn into the positive side of the battery. And so we call that part the electron flow, and we know that the conventional current is opposite of that. So we'll talk about this in the way of the electric potential difference. And so we're a lot of the times we're looking at the idea of how much potential we have in a certain spot and then how much potential we have in another spot a little bit farther away. And so the potential difference, or the PD, is the energy transferred when 1 coulomb of charge passes from one point to the other point. And so we're looking at what's actually happening in there as it moves from one place to the next. When we're looking at the specific IB verbiage, the IB will always use the electromotive force to talk about the voltage provided and the potential difference to talk about the voltage used. And so if you look at the Holt text, sometimes it'll just say you have a certain amount of voltage provided by a battery, and then it'll talk about how much voltage is used in a given resistor, or it'll talk about a voltage drop or something like that. The IB is going to be fine in the way that you might talk about something if you talk about a voltage drop or if you talk about your potential difference. But when they're asking a question, they'll usually refer to these in the way that is shown here. So if it's providing the voltage, it's your electromotive force. And we'll talk about that later when we talk about batteries a little bit more. We call that EMF. And then your potential difference is the voltage that's used, and that's represented as PD. So one of the details that we want to look at is this idea of how electricity is conducted in metals. And so we'll use copper for an example here. Copper is going to have, a copper wire has millions of copper atoms in there. And then most of those electrons are held tightly around that nucleus. What happens, though, is that some of those last ones are not held as tightly, and so they are able to be removed or move away from the rest of the atom. And so when the electrons leave, they're obviously negative, and it leaves a positively charged ion with the copper atom there. And so this is how metals are going to behave. And so because you have those electrons that are separate and then those positively charged ions there with the electron, or with the nucleus, the electrons can move. They'll be drawn toward another ion and then move away and then be drawn toward another ion. And this is what happens when we create the drift velocity of your electrons. And so they're slowly moving in a singular direction because of the way that the negatives and the positives are interacting along the way. And overall, that's driven by the negative terminal of the battery, and it's repelling the electrons from there. And then those electrons are drawn toward the positive terminal of the battery. The positive ions are not shifting because they are incredibly massive. And so even though they have a positive charge, they're not shifting away from the positive side of the battery because they're so much larger than the electrons. And while we were talking about this in the way of copper, copper works really well, but all metals have a structure like this of some sort, and some work a little bit better than others in the way of conducting electricity, but they can all operate in the same way. And so when you put that battery on the wire, and you have your positive and your negative. We talked about this a minute ago a little bit. They still have that random movement of the electrons and then the ions in there, that the electrons are negative and the ions are positive. But because you have the negative terminal of the battery repelling the electrons, those electrons start to move in a uniform direction together, and that's your drift velocity. And that's what is creating our electric current. So we have those electrons are moving, and then we have a current that is created at that point. And you can think about it like a current on a river. The water's going down the river, and the faster the water is moving, the faster the current is. And in this case, we're talking about the electrons that are moving, and yes, conventional current goes backward from this. But as they're moving, we measure that in amperes. We call that amps usually, and is using an ammeter. The ampere is our fundamental unit when we're talking about current, and it's measured using an ammeter. And an ammeter has to have the current passing through it so it can measure how many electrons are going by every second. And because it ends up being in series there, and because it's in series, we don't want it to mess with the rest of the resistance of the circuit. So we don't want to put it in an ammeter and all of a sudden have it slow everything down because it has a high resistance. So when we're talking about an ammeter, and we'll talk about this a little bit more later, the ammeter will always be put in series, and it has a really, really, really low resistance. An ideal ammeter would have 0 resistance on that. But what happens is the more current you have passing through there, the more electrons you have every second, and the higher current that's measured with that. So if you talk about coulombs, we've talked about coulombs a little bit, and we know that the charge on a single electron is 1.6 times 10 to the negative 19th coulombs. And when we're talking about the current, when we measure amps, an amp is measured in coulombs per second. And so if we look at that and we have 1.6 times 10 to the negative 19th coulombs, that means we've got about 6 times 10 to the 18th electrons going by each second. And so using that idea of talking about coulombs with the numbers talking about amps with the numbers that are a little bit more straightforward to use and can make a little bit more sense as we're doing that. But keep in mind that as we're talking about an amp, we're talking about just huge amounts of electrons that are going by in any given second because of that amp. So looking a little bit more specifically at how we're measuring current, it's our charge in coulombs divided by our time in seconds. So current is I, and so Q over T. And then the other way to look at that is if you want to know how much charge has gone by, you would take the current times the time. So just a rearrangement of that equation is what we're looking at here. Either way, the current is the rate of flow of that charge. And one more time about conventional current to make sure you have it. What happens is they used to think that the current was a movement of positive charge, and so because they thought it was a movement of positive charge, that would logically be repelled by the positive terminal in the battery and then drawn into it by the negative terminal. And then over time, they realized that it wasn't the positive moving there, that those ions were too massive to be moving throughout the wire, and so they realized it was the electrons and came to a point and said, oh shoot, it's backward. And they decided to keep it and then talk about it as conventional current. So just things to keep in mind. So this next part, we're going to look at resistance. And you looked at resistance last year, and the basic idea of resistance is what is causing that current to slow down and then to use up that power that's being provided there. And so if you talk about a tungsten filament versus some wire, tungsten filament has a high resistance and the wire has a low resistance. And so it's more difficult for the current to get through the tungsten filament. This happens because of the way the electrons move through the materials. When it's going through tungsten, there's a whole lot more collisions of the electrons than when it's going through copper wire. It's like trying to get to your locker by running through second floor or running through first floor during passing time. If you're running through second floor, you're going to run into a whole lot more people than if you're running through first floor on that. So when you're looking at resistance, it's always measured in ohms, and it's defined as the resistance of a conductor is the ratio of the PD applied across it to the current passing through it. So the potential difference to the current, the ratio between those two. And if the IB is asking about the definition of resistance, that's the sort of definition that they're looking for. They're not looking for an equation definition. The equation definition that shows up in your data book can be used to help kind of drive that verbiage for you, but know that they're always looking for that definition. But when you're looking at your resistor, you have your potential difference divided by your current. So with wires, we want to have a low resistance so the current can move freely. And with a resistor, we want to have a material that has a higher resistance, and so it can slow that down. Nichrome wire, it's a nickel chromium mixture that's commonly used. And this relationship between voltage and current and resistance is Ohm's law. And the way that, again, definition wise, Ohm's law states that the current through a metal wire is directly proportional to the PD across it, providing the temperature remains constant. And so again, if we look at the definition, if it says, oh, hey, we want the definition, we're not looking for V equals IR. The situation that they're asking about is this verbal definition here. But it's that relationship, that directly proportional relationship between the potential difference and the current that's going through it. And so that's Ohm's law. And what we've talked about up until this point is always materials that obey Ohm's law, and we call those ohmic conductors. And what we're going to look at the next part is the difference between an ohmic conductor and a non-ohmic conductor, and when those occur and how they are recognized. So in order to take the measurements that we would be looking for here, we would use a voltmeter and an ammeter. And a voltmeter needs to be able to measure the amount of voltage drop across a given component. And so in order for it to have the same voltage drop, it's hooked up in parallel to that component. Because it's hooked up in parallel, we want to have an incredibly high resistance on that voltmeter, so a teeny tiny amount of current goes through that. So much so that it doesn't affect the rest of the circuit. Same thing with the ammeter, but in reverse, the ammeter needs the current to go through it. And so we want to have a really low resistance on the ammeter so the current can go through it, but it doesn't affect the overall resistance or the way that the circuit behaves. So this graph represents ohmic behavior, where we have a linear relationship between voltage and current. And what happens is when you have a resistor that is exhibiting ohmic behavior, your current is directly proportional to your voltage. So regardless of how you have your V or your I, sometimes you'll see the graph where you have voltage on the x-axis and current on the y, and sometimes it will be reversed. But either way, when it's exhibiting ohmic behavior, you'll have a linear slope there. And that linear slope will either be representative of the resistance, or it'll be 1 over the resistance, depending on where your V and your I are placed on that graph. Looking at this graph again, you have V on the x-axis and I on the y-axis. And so as the voltage increases, the current also increases. And because of the way it's set up, if you look at the slope is rise over run. So rise would represent the current, and the run would represent the voltage. So the slope is I over V. And so resistance is V over R. And so the slope of this line would be representative of 1 over the resistance in that resistor. So this would be a case where it would be something that you could use in an IA to be able to talk about and be able to justify how your graph aligned with your research. A graph that looks like this is showing non-ohmic behavior. And what happens at just sort of standard situations, at low voltages and lower currents, you still have that ohmic behavior that occurs, but as you reach higher voltages and higher currents, your power increases, the filament usually starts to heat up. And in heating up, even as the voltage increases, the current isn't able to keep up with continuing to increase like that. There's too much resistance that's there. And so you no longer have that same ohmic relationship as you do at lower voltages and currents. And even as you can crank the voltage all you want, but the the current doesn't respond in the same way, and you're not able to get as much current going through there. At the same time, the temperature is increasing, which is causing more resistance, which is making it so the current can't get through as much as it would normally do. And this slide is just recapping what I was just talking about with that. And so it no longer produces an ohmic behavior, but because it gets hotter, the resistance increases. And so even as you're increasing the voltage, the current isn't able to keep up. And with the higher resistance, the current isn't as high as it would be in an ohmic relationship. And even though you can change the direction of the current, that graph will still look the same in the positive quadrant, and then in the negative quadrant. It'll be symmetrical for both of those. So one last thing to look at here is the idea of power dissipation, and it's kind of a mess with all of this, and so I'm going to break that apart right now. So let's take, this is a whole lot of stuff, let's break it down and see what's actually happening here. And we know that power is equal to work over time, and work is measured in joules. When we're talking about the work that's done on a charge, well, we know that voltage is, if we talk about volts, we have joules per coulomb. And so we know that voltage is equal to work divided over the charge, the amount of work per charge. And so we can rearrange that to get work by saying that work is equal to, multiply both sides by Q, our voltage times our charge. So that's part of what we have. We can put that in up here for our work. We also know that if we want to know how much charge goes by in a given situation, that our charge is equal to the current that goes by in coulombs per second times the amount of time it takes. And so we can take and rearrange that for time, divide both sides by I, and we get that time is equal to charge over current. So we know the total amount of charge that we want, and then the amount of current that's going by, so how much charge every second, and it would give us our time. And so we can take and put this in here. And so what that gives us, we know that power equals work over time. So we can say our work is V, our voltage, times our charge, divided by, and we'll say our charge over our current. And if we rearrange this, these cancel out. V, the bottom of the bottom moves to the top. And so we have P equals IV. And so that's where that comes from. There's another way that we can get there. The other way that we can get there is by saying that we know, using the same idea up here, that work is equal to voltage times our charge. And we know that Q equals IT. And so we had that part from up here as well. And if we take and we plug this in here, and we take and plug this part in for the Q, we have that our work is equal to our voltage times I times T. And if we go back and say, well, power equals work over time, put this in for our work, we can say that we have V times I times T over T. The times cancel out, and we're left with P equals V times I, or P equals IV. So the same thing, either way, we can get to the idea that power is equal to our current times our voltage. Another piece that we can look at that when we're doing this is this relationship between power equaling current times voltage and V equals IR. So in the IB data book, it actually gives you a couple of different rearrangements for power. And so sometimes they'll ask you to go between one and the other on that. And all you're doing is you're doing a combination of these two equations. And so we start with P equals IV, and we know that V equals IR. And so if we take and we put in V, IR for where V is, we have P equals I times IR. And so that gives us I squared R. We also know, so we have P equals IV again, and we have V equals IR. And if we rearrange this equation for I, we say that I is equal to V over R. And so if we take and we put that into the I part of the equation, we end up with P equals V over R times V. And so V times V gives us V squared over R. And so in the end, that gives us several different things. We have P equals IV, which is also equal to I squared R, which is also equal to V squared over R, which is also equal to work divided by time. And so all of those pieces are equal to each other, and that's how we get between each of them, both from the stuff that we did at the beginning and then the pieces that we have here.